Did you hit your head on it?
I will say though, one of the things that RPL prides itself on is heritage of the propellant that we use. It's passed down over the many, many years to the point where the guy who initially came up with it, Professor David Reese, is a professor here, therefore the professor part, and he's also a pretty big name in the entire solid rocket community, specifically the research side at Aerospace Corporation. And so as a result, it's because of the passing down of information, we've been able to create cool stuff like this. There's not a lot of other universities that are capable of doing this. It's not because we're more intelligent. It's mostly because we.
Well, that's part of it.
Part of it. I'm kidding. No, we just have a really good community of people who are willing to pass down information and learn from failures and fail.
It's always a shit show. Deciding which screen to mirror and which screen not to mirror.
Kaustubh, tell me a little bit about rocket propulsion.
Yeah, that's the whole point of this.
I know. Let's hear some. What you got?
I will say rocket engines were kind of, so I will preface this by saying I came into USC as a biomedical engineer, and rocket engines are one of the few things
and I
that...
poached him.
Partly. But partly it was me being an RPL and realizing that rocket engines are actually really cool. They don't just make a lot of fire, and I say that because a lot of people look at them like, wow, that's just a massive flamethrower. It's like, no, that's a lot of energy going through like a small hole and coming out of a bigger hole and pushing really cool things into space. It's just...
Yeah,
I got an A in physics.
Yeah.
Okay, yeah, so Kaustubh already said, I'm Adam, that's Kaustubh. Yeah, this is the first lecture for the semester. Thank you guys for coming. We're going to talk about propellers. It's going to be fucking lit.
Your face is in the way.
So yeah, this is where on the rocket we are.
Right
the
here,
rocket
that's the propellant part.
Yeah, so you can see this is Fathom 2. The rocket's about, by length, almost all rocket. So, Fathom 2 motor, Fathom 2 motor was about 60 inches long, with a nozzle about 70, and the entire vehicle was about 120 inches long.
Yeah, for those of you guys who ever carried Traveler 3 before the propellant was put in, you're like, oh, it's not that heavy, and then you put the propellant in, you're like, wow, it's really heavy.
Yeah. So Traveler 3 is almost 190 pounds of propellant. If you include the insulation systems and the nozzle, the whole thing all up weighs like 200 pounds, and then you're putting it into a 120-pound tube. That's quite a lot of rocket in there.
So, how do rockets work? Usually when you think of propulsion, when you think of things that are being propelled, they're usually pushing against something. A car has a wheel that rotates and pushes against a road. That might be wrong, but whatever. There is simply nothing to push against when you are in space, and especially when you're moving that fast. And therefore, the way rockets work is not by pushing against something, but rather by expelling mass. So this is going to be what kind of explains what the rocket equation is. It's simply a conservation of momentum. If you expel a certain mass at a certain velocity, that momentum is going to be transferred into your vehicle to push it up.
Yep, rockets are momentum transfer machines. That's a good way of describing them.
So these are some of the fundamental equations. How do you define the thrust of your rocket engine? The m dot term here is the flow of mass in kilograms per second through your nozzle or through anything in your body. Then your UE is your exhaust velocity, so how fast are you pushing that mass out? That's that momentum transfer part that I was talking about every incremental part of mass that you push out at a certain velocity, that momentum gets transferred as thrust into the actual vehicle. The second part here is it's a little bit usually less in most rocket engines. It's the difference in pressure between your exhaust pressure and your ambient pressure and the area of your exhaust plane, or sorry, your area of your nozzle exit plane. And that kind of gives you the change in pressure and then the resulting force. And usually that does hurt you a little bit, but it doesn't really matter.
Yeah. And these are called usually the momentum thrust and the pressure thrust. As a way of differentiating.
And for our rockets, the momentum thrust is very, very high.
Way higher.
And the pressure thrust is puny.
You can rewrite those terms as the UEQ here on the left side. And it basically ropes the UE part and the pressure part together, and you can express that as the C star and CF numbers.
Yeah, and these are the two numbers that are usually used as, there's a lot of numbers that can describe the efficiency of your system. One of those we'll get onto the next slide. But these are also one of the ways you can define it. The C star is your characteristic velocity of your rocket engine, and that's almost always a function of your temperature at which you combust at, basic flow that you have through an orifice. And then your CF is your actual thrust coefficient, which is a measure of how efficient your nozzle is. And that's also a function of your exhaust pressure versus your ambient pressure, and that includes the pressure force term as well. And the combination of the two gives you the equivalent velocity, which you can easily sub into that equation.
Yeah. And so we usually, you start off getting these numbers from a piece of software called CEA, which is NASA software, super great stuff. We'll have probably a CEA lecture sometime in the future. It is its own beast. So you kind of get started using that, and eventually you use experiment, and you can derive those values from experiment. If my screen won't turn off. There it is.
So this is the usual way to measure the efficiency of a rocket engine. I included this plot up here in the top left corner. Obviously, I don't know if you guys can read it, but the bottom red bar is the peak efficiency of a rocket. The x-axis here is the Mach number which it's traveling at, and then the specific impulse. And the reason why we use ISP only really to describe rocket engines and maybe in-space thrusters, but we don't really combine those two, is because that graph right there, you can say that your jet engine is super efficient, but that doesn't really count because you're not going that fast and you're adding air into your system. So I guess this is kind of what's used. The units are in seconds, which is not very, doesn't make much sense. The units of the way the Russians did it, which is meters per second, makes more sense, but the Russians did not get to the moon.
Yeah, so the divide by gravity term here is to make this number independent of your unit system, because we're in America and we use dumb units, freedom units, and the Russians and the British don't, and so we had this C star CF term that describes how good your rocket is, and everyone was using that. And we were like, it'd be great if it was totally unit system independent. So we divided by the gravity that we all know and love, and you get ISP.
So what do you do from your ISP? From there you can derive the actual delta V that you can get from your rocket. The delta V is the change in, or instantaneous change in velocity that you get from your rocket engine. So you can see that if you maximize your ISP, you maximize the efficiency, so you can have less propellant and more payload, which is usually what rockets are trying to do, is put payload in space, and higher efficiency means more payload. Now, that's really hard to do, increasing your ISP, because obviously rocket science is hard. There's a hard cap on how efficient you can get, effectively. And so that brings you to the third term here. GE is never going to change. This term right here is kind of the it's the ratio of how much propellant, the mass of your entire rocket before the propellant is burned up, divided by the mass of the rocket after the propellant's burned up. And so that number is always greater than 1, and that number kind of derives as to what your mass efficiency is and your mass fraction, or all sorts of numbers like that. And so when you're designing a rocket, you have to play around with this. You still want to maximize the amount of payload that you can get, but you also don't want to have to deal with having to design a completely new propulsion system. And so a lot of the ways that people size rockets and design rockets is they just accept that their ISP is the same. You can't really do too much to change your ISP, and so you figure out what your allowable mass fraction is, how much of your rocket has to be propellant.
Yeah. And you can see how, again, because there's an ln in there, it's be a rapidly expanding pain in the ass. For very large rockets, you can't just do it with one stage. You get around this, you cheat by using staging. You have one rocket that's basically entirely propellant, and then you burn that until it's complete, and then you throw it away, and then your satellite makes up significantly larger in the fraction of your upper stage.
Yeah, when you're designing rockets and you deal with staging and how to get around the delta V equation, it gets pretty nuts, and it does get very, very complicated. And there's a lot of different trades you have to do, which is pretty cool. So these are kind of this kind of introduction to what liquid rocket engines are. Usually, you'd probably be more familiar with liquid rocket engines if you're not coming from RPL. If you're seeing what's usually in industry, and so these are the two big types of liquid rocket engines. You have the American cryogenic way, and you have the Russian hypergol way. Once again, who got to the moon? Put that out there.
Yeah.
So I'll just go over some cryogenic propellant. So the theoretically most efficient combination of propellant is liquid hydrogen and liquid oxygen. You have a pure fuel in liquid hydrogen, and you have a pure oxidizer in liquid hydrogen, which
What?
sorry, liquid oxygen.
Liquid hydrogen does it all.
And if you remember how a fire is made, you have an oxidizer and you have to have a fuel and some sort of ignition source. And so that's the most efficient type of rocket engine. There are downsides. Obviously, if it's cryogenic, you have to cool it down. So now you have to include a cooling system, and every pound that you put into your propulsion system is a pound of payload that you lose. And it really starts to add up if you're at a company and you're like, I need to have a massive bottom line, and rockets are already kind of like a very slim profit margin industry. That how do you play around with these things? And the other option here is hypergulls. Hypergulls are super dangerous because they ignite on contact. That's kind of what a hypergull is. The Russians use it a lot because it's pretty simple to store. You still see some hypergulls in what we see on the next slide is an abort engine, and then also in space thrusters you'll see some hypergulls where you just flow this super reactive. Forgot what it was. Is it hydrazine?
Yeah, hydrazine.
You flow super reactive hydrazine over like a catalyst, and that creates like a little bit of an expansion of a gas, and that like propels you a little bit. It's like a super low efficiency, but it gets the job done because you don't need a lot of thrust in space.
So these are generally more efficient, and you use these when you really want to go to space. These are less efficient, and you use them when you want to have a liquid rocket whose propellant you can store and will work all the time. And there are only two scenarios for that. One, ICBMs. Two, satellites. And that's why they're only used for really anymore Russian ballistic missiles and satellites. Because they are so bad in every possible way.
Also, if you guys have any questions, feel free to.
Yeah. Actually, should we save questions for the end?
Okay, that works too.
Unless it's like really quick to clarify. Hopefully
No,
we
the
don't get the
monkey.
death monkey. Hopefully this works. Oh, maybe
YouTube
not.
is down.
YouTube is just down for everybody?
Yeah.
Yeah.
Wait.
What?
That's
Yeah,
nuts.
Okay, well at the end of this,
We've
we'll
been
try it
hacked.
again, and I'll show you guys this video. It's super cool.
The monkey's pretty cool too.
So this actually
They said the
was
world
tested at the
record.
test site that we do all of our testings at in the Mojave Desert, the Mojave test area. And it's the guy whose voice counts it down is a dude named Dave Crisali who's helped us out many times before in our solids testing, and will continue to help us out because he's
Also, with abort engines, when Adam was talking about hypergulls, they have to be super reliable. Like if your rocket is about to blow up and it is blowing up, you want to get your people out of there as fast as possible.
Like on Soyuz.
Rip.
So that's why they're like going. They go really fast. Usually don't use cryogenics for that.
Yeah. So the other type, the really common type of rockets, is solid rocket motors, which is the kind that we use. So they're of particular importance. SRMs usually, or always, you have a solid object, propellant, that has a mixture of fuel and oxidizer in it. A solid propellant that you're all extremely familiar with from your childhood is black powder in your fireworks. That's a solid propellant. It's the first solid propellant ever invented. Goes back to the 1200s. It's been around for a very long time. Extremely low efficiency, and it likes to blow up in your face. So we don't use that. The two common types nowadays are double-base propellant and composite propellant. And those lines have actually started to blur a little bit. But generally speaking, double-base propellants are a mixture of nitroglycerin and nitrocellulose, which are explosive, and some additives. They have really good ISP, and also you can extrude them. They're like a liquid to begin with. So it's really convenient for making high-performance rockets on the assembly line. So like air-to-air missiles, surface-to-air missiles. They're really good for missiles. We don't use these because they explode. And for really high-performance motors, you can include elements of a composite propellant in your double-base propellant, and you can get extremely high efficiencies. On that ISP side, Kaustubh showed, Rocket Lab rockets generally get 230 to 250 seconds of ISP, whereas double-base propellants or modified double-base propellants, where it's like a double base, but they add an oxidizer, and they add aluminum, and they add a little bit of RDX, high explosives, an energetic plasticizer, also some terrible things. You can get the ISP up into the 300s, which is what you would get out of a liquid engine. But then again, it becomes a class 1.1 explosive, and it goes off when you look at it wrong. So we don't do that.
REX is illegal
Yeah.
in India.
Yeah. So composite propellants, at the minimum, it's a powdered oxidizer and a rubber or epoxy binder. We use a liquid rubber binder called HTPB or R45. When you add it to a curative, it starts off as polybutadiene, it cures to a urethane rubber. It's got about the consistency of an eraser, a hard eraser. We add metal to it. You don't have to add metal. The rubber itself acts as a pretty good fuel. Adding metal increases your ISP a crap load. It also makes the propellant, by making the propellant burn hotter and having higher energy density because metals are energetic when they burn. They also have the added effect of making the propellant slightly more difficult to ignite because they increase its specific heat because you have metal in there. So it's kind of a win-win-win-win. They also make it opaque, which is important. So we use ammonium perchlorate as an oxidizer for relative low cost, and it's available in basically all rocketry. Everyone uses ammonium perchlorate as an oxidizer unless you're doing something exotic. You don't really need extremely high performance from a couple of the other classes of oxidizers unless you're doing missiles, and so we don't need that.
Oh, also, quickly to add to this point right here, to go from increasing your flame temp to increasing your ISP, the connection you got to make here is that you increase your C star. So remember when I was like, your C star is dependent upon your combustion temperature? Well,
there you go. So you can see how rockets have chemistry everywhere. You don't have to be super good at it. You just kind of have to have an understanding of how the physical things connect to the chemistry of it.
oh, also you can't turn off the solid rocket motor.
Well,
yeah, that's an
yeah,
important note.
allegedly.
Once you turn them on, once you light it with the igniter, it will stay on until it goes out, or until you blow
That
a
makes
hole in the
sense.
side of it with high explosives. So our rockets, once we light them, they will go, and they will continue to go until they've exploded or burned out.
We're gone.
Seen this.
Yeah. This is extremely familiar to all of you that went to the travel.
It's also one of the reasons why people don't use solids on commercial rockets all the time, because you can only burn for like a minute. If you burn for a minute, you have a massive booster.
Exactly. So on these rockets, you got to have nozzles. Nozzles, as Kaustubh said at the very beginning, super important to make the rocket part actually work. The way nozzles work, you burn a bunch of gas inside of the rocket. If it's a liquid rocket, your tiny chamber. If it's a solid rocket, the entire length of the motor. And the gas gets extremely hot because rocket, and it's very high pressure because you've confined it and you've restricted the space that it can leave through. There's a tiny hole at the end. And so this flow, when it gets into the nozzle, what's called the converging part, this sort of constricting bell part, it speeds up, and the pressure goes up. Actually, no, it goes down. Sorry, because you got to trade pressure for velocity. And what winds up happening is the flow speeds up until it gets to the nozzle throat. And at the nozzle throat, the flow is going the speed of sound in the fluid. And so an interesting thing here happens. Once this fluid goes sonic, when you expand it, it continues to speed up, which is not like a water hose works, where you squeeze the end off and the flow speeds up when you choke it off, and then it slows down when you let go of it. Because the flow is now supersonic, it can't communicate, it can't exchange information with the gas that's in front of it. And so from the gas's point of view, there's nothing in front of it, it's a vacuum, and it will shoot off into the distance at maximum velocity possible. And it trades pressure and temperature for velocity. And what winds up happening is it speeds up crap load, and by the time it leaves the nozzle, it's going supersonic, or verging on hypersonic, depending on the nozzle. So what winds up happening is you have extremely high speed gas, not very heavy, but because it's moving so rapidly, you get that momentum transfer. That's how the rocket works.
Also, keep in mind that something that's going Mach 1 isn't always going 343 meters per
Yeah.
second.
Note that I said in the fluid. Speed of sound is dependent on the fluid's temperature, and also its specific gas constant, and its ratio of specific heats. So these are things that you get from CEA. They're thermochemistry numbers that depend on the fluid's chemical composition and temperature and a whole bunch of other stuff. So nozzles get really hot because rockets are really hot. The inside of a lab solid rocket motor when it's firing is close to 6,000 degrees Fahrenheit, which is really hot. I can't really emphasize that enough. So you can't really just like shrug it in and say, whatever, it'll be fine. You can't just send it. So you gotta, for all nozzles, handle that heating problem somehow. Some nozzles use a lot of nozzles for commercial rockets use what's called regenerative cooling. They'll take the oxidizer or the fuel, and they'll pump it around the nozzle. This usually has the added benefit of making the fuel or oxidizer warmer, which means you get more energy out of it when you burn it. And then it cools the nozzle down, keep it from melting. So the shuttle booster, or the shuttle main engine, the engine SpaceX uses, the Merlin, around the combustion chamber, they do this. Most modern engines do this. You can also use a radiative or heat sink nozzle, which means exactly what it implies. You just absorb the heat and shrug at it and say whatever, send it. You can do that for small rockets, or you can do that on nozzle extensions with some very exotic materials with very large rockets.
Or
Yep.
satellites.
Exactly. So the upper stage of the SpaceX launch vehicle, the Falcon 9, uses a Merlin engine that has this big extension bell on it. And the first part, the combustion chamber and the first part of the extension are regeneratively cooled, but the bell is made out of molybdenum, which is this super cool metal. It's kind of expensive. It's super expensive. And when it gets really hot, it just takes it like a champ. It can be really hot and stay really strong, and it starts to glow, which is why the nozzle extension, if you look at the upper stage videos when they're flying, it's just glowing because it's radiating that heat away. It's reached equilibrium. For a solid rocket motor, you usually use these things called ablatives. Ablatives line the nozzle with a lining made of some type of chemical compound, usually phenolic, that when it burns endothermically and it chars. And so it carries the heat away, producing a layer of sort of cool gas. It reacts the heat away, and it makes a really high performance insulative layer. There's a whole bunch of processes that go into ablation. For a solid rocket motor, you really can't do regenerative cooling because your fuel and your oxidizer are solid. You carry around a water pump and a tank of water with you, which is wasteful. You can do radiative cooling if you have a tiny motor, but most solids use ablative nozzles. So ablation also protects the inside of the rocket. And you can see there's a lot of stuff going on in here. Ablation is a very complex process. It's very difficult to model, but it is the reason why our solid motors are even possible. Without it, we would be shit out of luck. It would be just a bad time. So the major thing to note here is that you're charring and you're producing these gases. And these gases, as you can see here, thicken this boundary layer. And they basically protect everything downstream with cooler gas, and in the process, react heat away, physically carry it away as gas and as eroded char. And the char itself is pure carbon, which is a very good insulator. So it's pretty awesome. That's why the nozzles are called torched and shit when they come back after we fire them. So yeah, solid rocket motors. There's not a lot of solids are somewhat more difficult than liquids to explain what's happening because they are a high pressure, high temperature black box. You can't really look inside of them. And there are lots of multi-phase flow things going on. It spans very large scales of energy, pressure, over very tiny length scales. So it's difficult to model. But thankfully, someone in the 50s or 40s or whenever had a plot of pressure and burning rate, and they said, man, that looks like a power law, kind of. And so now we have St. Robert's Law. This law has no basis in the actual first principles of what's happening. I cannot stress that enough. This is not a description of a physical phenomena. It's just, it tends to fit for most solid propellants. That your burning rate is proportional to the chamber pressure raised to the end power multiplied by some number A. It works really well for a lot of solid propellants. Actually, it fits almost perfectly for most of them. Some at higher pressures or lower pressures doesn't quite work out, but for us, it works really well. N is what's called the pressure exponent because it exponentiates pressure. It describes your propellant sensitivity to chamber pressure. A is a temperature coefficient, and it describes how sensitive your propellant is basically to what temperature it starts at. If your propellant gets really cold, it'll burn slower. If it gets really hot, it'll burn hotter, which is actually a real problem for motors in industry. Something you have to take account of when you're launching the shuttle out of the Cape during the wintertime, the booster's 40 degrees. But in the summer, it's 100. And those things can cause a 20% variation in motor performance. The motor will still burn. It'll get the same total impulse out of it about, but it'll burn either slower at lower pressure or higher pressure in a shorter period of time. And if you don't take account of that, you're going to have a bad time. So these two numbers you get with static fires. You can only get them with static fires. There's no way to get them from theory. You cannot take a new propellant, mix it up, say, oh, it's got 70% ammonium perchlorate, 10% aluminum, this much oxidizer or this size particles and this binder, N is going to be 0.3, A is 0.03. That's not how that works. You can't do that. It's impossible. It's still one of the fundamental limitations of solid rocketry.
That would also fall from what St. Robert's law is. It's not an explanation of any theory. It's a kind of, here's a curve fit.
Yeah,
Curve
exactly.
fit works.
It's just a curve fit. But using the burning rate, you can get this pretty awesome equation. This equation relates the mass that's being generated by burning propellant, which is the burning area, the burning rate, and the propellant density, to the mass that's leaving the nozzle. The chamber pressure times throat area divided by C star. It arrives again. So these, if you put R dot in here, you can solve for this in a MATLAB iterative equation, and you can, if you know propellant density, a burning area versus time, the R dot, you can compute the chamber pressure, and then you can figure out how much thrust and how much pressure your rocket gets over time, which is super convenient. You got to start off with experimental data, but once you get some curve fits from it, you can model any rocket using that propellant approximately, which is pretty dope. Also, of note, that N number, just based off of this equation, can anyone guess what happens if that number is greater than 1? Peter gets it. It's exponential, and it'll explode. So for all propellants that are not explosives, so explosives have this, but for all solid rocket propellants that are of practical use, N has to be less than 1, always. Yeah, so for exactly, energetics on explosives. If it's 0.3, if it's 0.8, that's fine, but if it's 1.2, it'll blow up, or it'll blow itself out. When you light it, any variation in pressure, the propellant will amplify, and it will run away from you. Whereas if it's less than 1, any variation in pressure, it will want to stabilize around some equilibrium point, which is, again, really convenient. So we use solids for a lot of reasons. They're easy to make. They're, well, relatively. They're pretty straightforward to handle. The case before you put propellant in it is just a giant tube, and then afterwards it's a heavier tube. The propellant itself is about as difficult to light as campfire wood, so it's kind of inert basically, without going at it with a blowtorch.
None of us have tested that.
Yes.
None of us have tested that.
We have actually, funny enough. Blowtorch does not set it off.
Yeah, so it's reliable. Once you light it, it will go. It will always go once you light it. It's relatively easy to ignite, and it's plug and play after you mix the propellant. You just shove it into the case. It's easier to design than a liquid system physically. Liquid systems, you have to have pumps and valves and all sorts of tubing and an injector, whereas this, it's a bunch of weird logs of rubber in a pipe. It's high mass fraction, so you get a high thrust for a given shape, which is important for making our rockets go to space. And we have a lot of knowledge about it. Lab has been making solid rocket motors for almost 13 years now. We've been doing this for a long time. It is our bread and butter. We know how to do it, and we know how to do it really well. And we've actually, successfully Sally-fired and launched a space shot motor. For those of you that don't know.
You might remember.
Yeah, you might remember that. So we can make the largest solid rocket motors of any amateur group currently in existence. That's pretty important to note, and it's pretty fucking cool. We can do it. No one else. There's only one other amateur group that makes rockets as big as we do, and they started a company, so now they're professionals. And none of the other amateur groups can use composite cases, carbon fiber cases on the scale we do. That's also important to note. That's extremely difficult to make because of the insulation concerns.
And we're also,
And we're also students at the same time. The cons of this, you have a high mass fraction, so you get high thrust for a given envelope. So the rocket accelerates a lot. Traveler 3 starts off, leaves the tower, pulling about 10 Gs. That would kill you. It burns out pulling 25 Gs. That would really kill you. So it's a pretty rough environment to put the GoPros and the electronics through. And it's a lot of structural loads. So, unfortunately, the way our rocket motors currently work, the propellant that we currently have, and the geometries that we can currently use, by necessity, we're going high thrust. The nozzle environment in the solid rocket motor is pretty brutal because you have molten aluminum in there, molten aluminum oxide. That stuff is bad. It has high heat transfer, and it also causes physical erosion. Unlike a gas floating over your wall, getting slammed by a droplet of molten aluminum at 1,000 feet per second is significantly worse. So nozzle environment in the solid is harder to make work, and thermal protection system that protects your case is also harder to make work than a liquid rocket engine. because rocket engines are, liquid ones are tiny, right? Small, compact objects. The combustion chamber on the Merlin engine that SpaceX uses is about this big. And so you can cool that relatively easily. For us, our combustion chamber is 81 inches long, and you have to protect all of it. If you burn through any of it, if you go through the insulation, carbon fiber fails at 300 degrees Fahrenheit. So we have a significant insulation problem where you have to stop 6,000 degrees Fahrenheit over a quarter of an inch. And it's not easy, and it took us a long time. There will be a lecture about this on Friday from the former lab lead Carter Allen. I highly recommend going if you're interested in how the lab made rockets not explode.
In addition to one more point here is that the altitude record for a liquid rocket engine is about 14,000 feet, and the altitude record for a solid rocket
380,000.
Huh?
380,000.
By university standards, in-house is 144,000 feet.
That we can prove.
Plus or minus.
Too soon.
Yeah.
Plus or minus 200.
Oh, the monkey!
I have this on Google Drive if you want me to show it at the end.
So this is the Traveler launch video.
Traveler
You
1.
might
Traveler
remember.
1.
Yeah, Traveler 1. So propellant geometry is an important part of the solid rocket motor. It's the only part that we can actually control
How the hell
besides
do
the
you
propellant
rocket
chemistry.
It's
So
at the top. It's a pain in the ass. You don't do that.
So you can make different shapes of solid rocket propellant. That controls how much thrust you get. Hey, Rob.
Shh.
So it controls how much thrust, how much pressure you generate over time. It's the only control you have over your thrust. Solid rocket motors, in addition to not being able to turn off, cannot be throttled. You can't change that thrust or pressure over time. Whatever we go with, we are sending boldly somewhere. And so these are different shapes. The ones that Lab uses, it's kind of similar to the tubular shape. So propellant pieces are cast into what's called a grain. A grain can refer to an individual piece. Lab makes individual grains. They're about this long and about this big around. It's basically a slug of fuel. In industry and in extremely large high-performance rockets that amateurs make, you'll see propellant cast directly into the case itself. It's called a case-bonded motor. Case-bonded motors, you don't have to put as much stress on your insulation because the propellant itself is the insulation, which is pretty cool. Case-bonded motors, kind of by necessity, can't really do a tubular grain because that thrust trace is, holy shit, progressive. And in addition to this is just the thrust. The vehicle's mass is going down over time, so your acceleration is even more exponential, which is a bad time. Star grains, really useful for case-bonded motors. Very, very, very useful. So when we refer to things as a finicil grain, and you might hear that term thrown around lab in the context of a case-bonded motor, finicil grains are fins on a cylinder. So it's tubular, but it has these slots coming off of it as well. And that's something we're working on sort of in the future. So Lab uses Bates grains. The Bates grains allowed, basically it's tubular, but it can burn on the ends as well. Because the ends can burn, you can put in a bunch of pieces of fuel. Generally speaking, more grains for a thing slick in the motor makes your motor more aggressive because the burning area is dominated by the ends of the grain. Because the grain ends and the grain port can burn, imagine the port, as its radius gets bigger, the burning area goes up, and from a previous couple slides, we saw burning area going up makes pressure go up. Whereas the ends, because they're these annular discs, as the radius goes up, their area goes down. Also, because the ends are burning, the length of the port in the middle is getting shorter. So you can make these things balance out and be basically flat, which is pretty convenient. Larger initial port diameters are generally more regressive and less erosive as well. Longer grains, sort of the corollary to the more grain statement, a longer grain or fewer grains makes your motor more progressive. So we say progressive and regressive. Progressive means your thrust goes up over time. Regressive means it goes down over time.
Other way.
Wow. So you can't see it super well, unfortunately, the way this is illuminated. But this is the Penetrode and Penetron motor. It's the first motor they fired for the Traveler 1 static fires. They both exploded. They have the same port diameter down the length of the motor. This motor is actually longer than the Traveler 3 motor that we've flown. It's a dumb motor. It's a really dumb motor. The Traveler and Traveler 2 motors, the port is wider on these grains than it is at the head, and that's to allow the flow to expand and to reduce this thing called erosive burning. This one I can show you.
This is my favorite video that our field
So erosive burning, before I show you these slides, erosive burning basically, what winds up happening, if you go PowerPoint DJ a little bit, because the end of the motor, you have all of the burning gas, all of the mass that's being generated by burning these propellant pieces at the forward end has to go down this tube. And by the end, this is the motor sim from traveling. This is what the traveling motor does. So we can estimate chamber pressure, we can estimate thrust, we can estimate the burning rate as well in each piece of propellant. So the erosive burning rate, you can see here, and the total burning rate. Erosive burning does not dominate, which is good. You don't want erosive burning to be really high, or else you're going to have a bad time. But the the reason why the motor sort of has this ramp and then flattens off is because the grains have different sized ports, right? There's 5 grains that are not capped. For those of you who've seen the cap grain before, you know what I'm talking about. For those of you that haven't, the forward grain on the traveler motor has a radius cap of propellant, and to protect the forward closure, the propellant at the top acts like an insulator, kind of like a miniature version of a case-bonded motor. But the bottom grains, because they have these different diameters, they burn out at different times, and their burning area over time is slightly different. And so you can see the resulting chamber pressure curve kind of like it flattens, and then you have these steps as the grains burn out sequentially. So
what are we doing
yeah.
for the rest of the year? We have 2 big things coming up. The first one is obviously make the entire motor for Traveler 4, which is a lot, but isn't that bad. We go out to a place called Squadron. We make propellant. And it'll be a whole day thing. It's super fun. Get in and out afterwards. You don't really get to go too much in and out around here. Yeah. And after that, we integrate a whole cartridge, and then we may put it inside of the rocket. Once that one's done, we have a full rocket. And so that's really exciting. And the other really exciting project we're doing, which is what some of the sophomores are working on, is a sophomore design vehicle. And we'll be testing out a completely new propellant formulation. The main goal of this project is to make the propellant pourable. Right now, when we make our grains, we basically have to roll it into little balls and then pack them into a grain. Sounds really dumb, but keep in mind we make the biggest motors.
Only make good motors.
And one of the benefits is that once we nail down pourable propellant, it opens up a whole new amount of different work that RPL can do. The things that Adam mentioned, such as Finicil grains, the star geometry, case-bonded motors, those aren't really possible with people dropping balls into balls of propellant and packing them with the G10 rod. Yeah. That's what cool things like portable propellant gets you. And one of the ways you do that is you have a bimodal distribution of ammonium perchlorate. Right now we use a single particle size of ammonium perchlorate, and one of the ways you can achieve portable propellant is by playing around with that ratio and seeing what works best, and then changing a few other things in the chemistry. Yeah. And so that'll be a really cool project, and once that rocket is done, hopefully we can go further and make the portable propellant even better and use that as our new propellant formulation. Probably won't be here for that, but...
Yeah, so the portable propellant, the sophomores, it's super exciting. Here's a good picture of what bimodal does. So this is one size, like glass ball, smaller object. When you mix them together, you get higher density. You can increase your density by like 20-something% going to a bimodal particle distribution. That's like packing apples into a cylinder. There's a lot of free space. You pour sand in there, you fill up that free space.
Actually, Justin and Ava, you guys want to say a few words about your project? Build a sophomore vehicle?
I feel like you said a lot.
Too much, maybe.
One of the things that Adam was saying was for the St. Robert's burning law, to figure out your A and your N, you need experimental data to figure that out, and then you can model how your prop works, or how it burns. So the idea behind sophomore design is that we're going to make a bunch of kiwis, which are 4-inch diameter grains, instead of our normal 8-inch. So they're going to be super small, and they'll burn very quick. And we're going to fire a bunch of those over a weekend in Mojave, and then get all the data necessary to model new flight. So that's what we're going to be doing for the rest of the semester, and maybe the first part of next semester.
It's going to be nuts.
yeah, there'll be a lot of really cool stuff going on. Eventually they'll make a static fire for a flight motor, and then they'll fly it. And it's really exciting. This is a whole new world of propellant.
I just wanted to add on to that software design project is super cool in that the main goal of Traveler is to be our space shot, but then after space shot, then what, But the cool thing about sophomore design vehicle is that it's a great outlet to do research, especially if you're an undergraduate. So being there at the ground level, going to casting trips, learning how to machine, because there's casting hardware, we need a machine, parts of the rocket, we need a machine. Learning how to acquire all that data during static fires, it's very valuable knowledge. And if you're there at the ground floor, then it sets you up well, so that when we're, big boy juniors and seniors, we can handle design and implementation and follow through process.
Also, I will say that casting is one of the coolest things ever. It doesn't sound that
Pretty
cool,
neat.
but that's kind of what got me really into propulsion, was because you get to kind of make propellant. Not a lot of people can say they've made rocket propellant.
Yeah.
So make sure you come to at least one casting session before you leave USC.
It's really a unique thing. We do it on a scale that really nobody else does, no other amateur group. Well, some other amateurs, but really no other college does it at the scale that we do. And you get to go to a professional facility and hang out with some cool actual professional rocket people, and you get to sort of wizard alchemy this mix of powders and weird liquids from nothing into this weird sticky black grayish mix that is rocket fuel. And at the end of the day, you've made something truly lit. So hopefully not lit. You don't want to die. But for those of you who are interested in casting, we'll be sending out emails about that relatively soon. We have a standard operating procedure we'll send out as well, so that you know how to do it without killing yourself. It's really exciting times. So, yeah.
I have some videos that we can actually watch.
Okay. Yeah. Before that, does anyone have any questions about anything we talked about or any important things that we didn't cover?
What is the process by which you static fire to test propellant values for A&N?
Yeah, so the way you kind of want to do it is you curve fit it, right? So you have two things. You have your burn rate, and then you have your chamber pressure, and you can measure your chamber pressure. And so from there, you can slowly take a bunch of data points and then plot them on a log-log scale, and it'll be a straight line. And then from there, you can get your exponents from there.
And if you have a bunch of static fires, you can do this one of two ways. You know the surface as it burns over time, you know what the initial dimensions are, and you know how that equation, or how the shape changes as you change some of the lengths. So you can basically fit your pressure curve to an estimated burning area curve. And even if you don't do that, you know what the thickness of the propellant is. And so you can say it burns out this thickness in this amount of time, and so the burning rate has to be blank. If you have a bunch of static fires, you pull all the data together and you can curve fit out what the burning rate should be from it.
It's also obviously much easier to do that when you have smaller 4-inch kiwi grains rather than a massive traveler size motor.
Where there's a bunch of different grains of different dimensions that are all burning and have erosive burning and this thing called the hump effect that I didn't talk about, a couple other effects that'll sort of pop up at the large scale. Small scale motors, there's only really one thing going on, and that's pretty convenient.
So
I'll go again if no one else has a question. So when you're doing these static fires, say it blows up because your end happens to be above 1.
It won't.
It won't?
No.
It'll blow up for a stupider reason.
Yeah. Yeah, the case that we fire them in is a solid aluminum inch-thick case. Really difficult to blow that up, and the closures will blow out before then. 2, unless you seriously fuck up, you can't make a AP aluminum, or some APCP propellant, ammonium perchlorate composite propellant, that has an N greater than 1. It's fundamentally not a thing because of the chemistry of the things that you have burning in there. If you spike it with high explosives and you put it in the oven, you give it some micro cracks, maybe, but we don't do that. So.
Yeah, one way to look at it is that not everything that explodes has an exponent greater than 1.
Yeah, so you can, a good way of, Kaustubh said, if you had if you put the propellant in a closed off cylinder, it could explode because the pressure would be eventually higher than the cylinder can constrain, but that doesn't make it an explosive. explosive generally, in the common parlance, refers to high explosives, which burn faster. Their burning rate is higher than the speed of sound of the material, which is like 8,000 meters per second. So yeah, they detonate. Detonation is different than bursting a sealed pressure vessel, which our propellant can do if you mess up the motor design. But generally speaking, we don't detonate.
In the past, lab has used additives in order to reduce the burning rate of motors that were seen as progressive. Have we ever experimented with using more grains for the same kind of fixed length in order to make it?
Yeah, so the Dutchman motor, I believe, had a bunch of tiny grains in it. Motor design is something you iterate on when you're designing a vehicle. You kind of have to go into it with what am I looking for, what are my ergodynamics approximately in the first place, what kind of total impulse do I want out of this, how high do I want the rocket to go, and then when you put some constraints on the aerodynamic environment that you want to see, the acceleration you want to see, those kind of things, you can, from those requirements, back out the kind of motor that you want. There are a lot of different motors that you can use to arrive at the same vehicle going to a certain altitude. It's mostly mission to mission dependent, and you kind of go through that process. You experiment with like a generally progressive, neutral, and regressive motor, see what those do for you, and then you can do variations on those themes and work your way into what the final motor design is. Any other questions? Also, for motor design and a couple other sort of more technical elements of the solids process, we'll probably have some additional lectures, more informal ones, maybe after general meetings or other times during the week going forward.
Out of curiosity, how many of you guys are astronautical engineering? It's a lot.
Nice.
So you guys are going to get to take a really cool class called AST 470, and so this will be your first introduction, I think, to rocket propulsion. And then after that, you get to see the whole course on rocket propulsion.
Yeah.
Kaustubh will grade you.
Got
Okay.
it.
Do we guys have other questions? Anyone? All right, we can watch some videos.
Swag. There you go. They're just gonna grab my finger and shake it. That's for engineering. What's that spacecraft propulsion? Your senior year. You'll learn a lot about. Yeah, you'll learn it first semester, senior year.
Is Neil filming?
Oh,
Learn it first semester, junior year.
Okay, also, highly recommend taking Astro 470 first semester of your junior year.
You have to have senior standing for it.
No, you
Does
don't.
not.
I don't have senior standing.
Wait, really?
Oh ho ho!
I just
You
told
just have
them
to
don't
ask.
want to say.
Oh damn!
He
Never
doesn't
mind.
have senior
Never mind.
standing.
So,
No one knows what the astro
highly
department
recommend
does
taking it,
anymore.
because there are some electives that you can take your senior year, depending on what year they're offered. There's a class taught by the man himself, David Reese, that Rob and I took last year. It's offered every other year, called ASTE 599, Solid Rocket Propulsion.
There's also AST 572, which is Advanced Spacecraft Propulsion.
AST
For-
570.
For
liquid
reference,
propulsion.
AST 470 is spacecraft propulsion, so
Very
obviously
cool
you can tell
classes.
which class.
There's also a
is.
liquid propulsion class is taught every other
570.
year. So if you're a sophomore right now and you want to take the solids class, you want to take the advanced spacecraft class, your junior year, you have to take 470 fall semester of your junior year. I would highly recommend doing that if you have any interest in solids. That class is one of the coolest classes, if not the coolest I've ever taken at USC.
Also, also take Astro 291 and then 491 twice. It's
Yes.
like a 1 unit elective that's on Fridays during our general meetings because the whole class is just Rocket Lab.
And you
So you just show up pretty much and do some work, and then like you'll get a good grade. And then if you do 3 of them, you get rid of a tech elective.
Yep.
It's pretty neat.
Yeah.
I recommend that. So
Nice.
Radovich pointed out to me there's also 2 500 level combustion theory classes in the AME department. It's like 513 and 514. Super cool looking stuff.
Yeah.
I'm stoked taking it.
Moral of the story is take every
Available
class
at
you can as
USC.
early as possible.
Yeah.
Yeah.
Graduate in 3.
Anyway.
2.
Anyway,
One.
here's Graveler.
Here's the Graveler
You've
too.
probably seen it, but this
Yeah.
has some. It's slowed down also, which is kind of neat.
Graveler stands for ground traveler.
Stands for, yeah.
What the? Just randomly skipped. Alright, well watch. But yeah, Ground Traveler was the space shot motor. This is the.
It's called Graveler 2 because Graveler 1 was already done, and then I believe they
And it's a stupid
did one
one.
else.
Graveler also metal base.
Ah,
Okay.
metal base.
yeah.
Remember when we tried to take?
So this was the largest successful firing of a amateur rocket inside of a composite case ever.
Yeah. So this the composite case technology differentiates the boys from the people who are actually making the magic happen. This thing is basically a missile motor. It is.
That's where
David Reese, after he fired it, came up to us and was like, "Yeah." What the next day? He's like, "Yeah, I talked to the people at Aerojet. I showed them the video. They were like, what did you tell them? Like, what did you tell them?" They're like, I didn't tell them anything. It's like this is. So they make this motor called the Gen 60, which is graphite epoxy motor, and the diameter. And it's like they made a Gen 8. We made a motor that they actually send to space for space boosters. It's a really cool thing, and it's in maximum slow mo.
This is how you decrease your burning rate.
Time speed.
Yeah, you decrease your burning rate by going to slow mo.
We're experimenting with spear propulsion technology. It's not working out very well. The targets just get destroyed.
Look at that mock back.
Yeah,
Yeah, you can see it expand a little bit as it comes out, and then the air pressure around it pushes it back together, and then
It's almost like colliding flows too.
yeah.
That's really neat.
Can you talk a little bit about some of the instabilities that are in the big exhaust train?
Yeah, so the little flickers you've seen, the flashes, are a combination of soft spots in the propellant, or just a little bit of uneven burning in the propellant being spat out. Also, the liner that lines the casting tubes the propellant mixed into, when you put an adhesive on it, that's basically the R45 rubber mixed with glass microspheres. And so as the propellant burns away, you're exposing that surface of the liner, those little bits will get ripped off and shot out, and they flash whenever they go out in the motor. If you looked at the startup, we'll have a different view of the startup, I think, in quarter speed. When the motor comes up to pressure, because it comes up so rapidly, the motor oscillates a little bit, which is sort of normal behavior when you slam the thing with the igniter, and it stabilizes at its normal operating pressure. And so a little bit of flickering. Also, at the very startup is aluminum slag being injected. When you light the motor, once you light it really fast, like we did for the Traveler flight, you wind up with a little bit of the motor burning at lower pressure. The igniter baggie itself is made of propellant and burns at lower pressure. And so when your propellant doesn't burn at high pressure, it creates more aluminum oxide and more aluminum as combustion products. And that slagging eventually gets spat out of the motor pretty violently. And as we see, there's this big couple of flashes coming out.
Obviously, slag's pretty bad because A, it's the molten pieces of metal that are flying through your rocket, and then also that's just lost things that you could have burned.
Yeah.
Like every piece of aluminum that goes out of your rocket is aluminum that wasn't burned and combusted.
SRBs. Yeah. On the shuttle SRBs, they end up having, like, when they recover them, about 2 tons of just like slag left over in them.
Yeah, because the way the nozzle works in the SRB, it's actually inset inside of the nozzle, or inside the motor, so that it can gimbal. So you have this little, like, basically U-shaped pocket, like annulus around the nozzle that just puddles slag. So they have to drive the nozzle in flight with a hydraulic actuator with a puddle of molten aluminum just chilling down there, which is a terrible problem for your insulation and a terrible problem for your control system because you're sloshing.
So this is a video you've probably seen, but I wanted to highlight the really fast ignition time because Adam put a lot of work into making our igniter more effective.
Yeah, there's some science magic ignition sizing equations to do.
So you saw the other one took like 20 seconds, no, 5 seconds to light, 2 seconds to light. This one just went from off to on.
In about 20 milliseconds. So, like 2 order of magnitude direction ignition time. Which is pretty sick because this means it's this is how they do it in real life, you know? They just like 3, 2, 1, it's not just like sitting there like, is it gonna do it? It looks fucking sick.
Wasn't Fathom 2 like, what, 20
Fathom 2 is
seconds?
Long enough that I had to cut it out of the
Fathom 1 was
video.
a 13 seconds ignition transit. Eventually, also, if you go back, Neil, place it over again. For those of you, like you said about the sort of instabilities, when the motor lights, because you slam it with this igniter, the entire combustion chamber is a pipe, and it resonates like an organ pipe. And so you can see the plume here is pulsing, it's flashing pretty rhythmically as the motor is oscillating as it comes up to steady pressure. And so the whole case has this acoustic way of traveling up and down it. as it's turning on, which is pretty cool. It's good that we didn't make the motor unstable, because that would have been a fucking bad time. A real bad time.
So are there any algorithms that are running for resonant tuning?
Yes.
To make it or as non-nodal as possible?
Yeah, so that's a thing that you have to deal with it in industry for larger motors. For motors our size, combustion instability, if you're operating, inside of if you're operating well above the minimum combustion pressure for your propellant, below a certain pressure it just won't really burn that well. If you're well above it, especially for propellants that have aluminum in them, there's not really concerns about combustion instability unless you're operating at extremely high pressures. Generally, you just don't have to worry about it. In larger motors, they do analysis to see if there's instability problems, but the aluminum, because it's semi-molten in the port, helps to damp those acoustic waves, and the complex geometry helps as well a little bit. It is a concern though, and also, even if it's not unstable, just the acoustics in the motor can modulate combustion, and that's something you actually have to think about for very large motors. The SRV, there's several different orders of like transverse and tangential acoustic modes that are in there, just chilling in flight, and they affect the way the motor burns. Thankfully, we're not making the largest motor ever made, so we don't have to worry about it. But it is a cool sort of academic analysis to something I need to talk to Dave Reese about, show him the video and say okay, if you light it with this transient, what kind of combustion phenomenon do you see? Because he's way smarter than I am at knowing that stuff, so hopefully he has something to contribute. Otherwise, it's just a cool video.
The last thing I wanted to show is just a overview of our propellant manufacturing. This is a video that I'm going to be posting at some point.
I've never seen this either.
But this is 90-second video, or 70 seconds, so yeah.
Don't send this to
hopefully the sound is working.
You'll be sent to.
So the motor for Traveler 3 was one of our largest at that time. It's about 180 pounds of propellant. We mix it in a facility out in the desert, which is managed by the company Exquadrum.
We follow a recipe that was created over many years. It started off when the lab was first created. One of the guys is a professor here.
Jesus.
And by iterating over that process, we were able to come up with a propellant that rivals some propellants made by other companies.
We buy all these chemicals ourselves, we ship them out to our facility there, and then we mix the whole thing from scratch. The tubes that the propellant goes into are machined here in our lab on the lathe, and so we really start with just the basics and build a motor all the way up from there.
While theoretically, you only really need to go out 3 times or maybe 2 times to make this whole motor.
That's the rolling into balls.
We spent our whole year basically casting propellant, eating in and out every week. And it worked out because now we have propellant, and hopefully that propellant will take us to space.
Good. That propellant did.
Very cool.
Can confirm.
Brandon?
Oh, that. Yeah, that and the nozzle.
And this is supposed to be the plume.
Yeah, this is fire nozzle. It's all
if you were sitting behind the rocket, this is
This is what it would look like here. I mean, it looked like that for a very brief amount of time.
Well, no, it would say "Have a nice day."
Yeah, exactly.
That's what it would say.
YouTube, if it's still up.
It's up now.
Okay. Wow. YouTube has some questions.
Why is Wi-Fi slower than Ethernet? Let's watch that.
So this was the what happens when you do it wrong video I want to show you guys.
Oh, show the do not like video.
Do not like.
That's a side note, but that's a good video.
Do not like.
So that's what happens when you make the motor wrong. You blow it up. That was Traveler 1 for you.
It was there and then it was not there.
Yeah.
Wait,
that was Traveler 1.
That was T1.
That's Traveler 1.
Yeah.
We found a piece of Traveler 1
parachute
back up in the
That's. I should mention though that this is higher than some university teams have ever.
Oh, this is higher than.
Yeah, we fuck up good.
That was about higher than the liquid rocket record.
So what happened on Traveler 1?
It's a boost
is plugged to the casting tube properly. Also, yeah, that fucking pitch off the tower. Go flush when it's windy.
Well, I mean, that's not what did them in.
Listen to the camera. But like, yeah, watch the vehicle coming off the tower.
Dude, go into slow-mo.
That's why
Look at that self-stabilization.
Yeah, look at those 4 fins working like.
No, it's the other one. The one that's
dude.
above speed. That one.
I've always been a 3-fin person.
What if we can just get rid of one of those?
So the root cause of the vehicle exploding was the propellant wasn't bonded to the casting tube using the inhibitor stuff that I mentioned earlier. So the propellant under acceleration loads and rotational acceleration loads in flight peeled off the casting tube, and you now suddenly have a whole lot more burning area exposed inside of the motor. And you can imagine that if your burning area rapidly increases, your chamber pressure rapidly increases. And if the motor doesn't explode, it would eventually equilibrate at a new higher pressure. But the chamber pressure went up, 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 and eventually burst the case at like 2,300 psi. So this is in slow-mo.
How did you determine that was the case?
Because they saw the propellant back on the ground with obvious backside burning.
Also, that grain was called Mr. Slidey.
Yeah.
It was sliding. As you can see, QC standards have gone up a little bit.
Yeah.
Just a little. Just a smidge.
So yeah, it comes out, catches the wind, pitches over, and then it has to pitch back, and then
it has to explode because of destiny.
Do not lie.
Yeah, you can hear Jordan in the back.
Last video, I promise.
Yeah, that's a good one.
Oh yes, please. Hey, everyone gotta be quiet for this one.
We use single stage rockets. This is not a single stage. This is a 2-stage.
Wait. Pause.
It'll take a second.
Yeah.
Elon Colorado, 54 to 30 on Tuesday. And ES 0300 for Aerotech 0280. Heads up flight is going in 5, 4, 3, 2, 1. Do not like, do not like, do not like.
That's what David Reese got because he tells me do not like.
Perfect.
Do not like.
You can't see his early frame. The motor flies over another crowd of people. So, yeah, we were
one of those
from the boy wonder David Reese.
Yeah, one of those people.
Cruise missile.
So that's why you don't use 2 stages.